Alright guys, so our last topic is potential energy diagrams and catalysts. I'm going to include them in the same video because catalyst is pretty short and simple. Alright, so if we start with collision theory, it says basically that for any reaction to occur, two particles must collide. And so when they do that, they have constant random motion and they're having elastic collisions, so momentum and kinetic energy is conserved. Alright, so the biggest thing is that they have to collide for a reaction to happen. Not every collision results in a reaction though, so there's two things that have to be satisfied before a reaction can actually happen. So the particles that collide have to have the correct orientation or position so that bonds can be broken and formed within that collision. They also must have enough energy when they collide, so they have to be moving fast enough for the energy to be transferred into from kinetic to potential for a reaction to happen. Alright, if they do not have an effective collision, they just rebound elastically, bounce off one another, and continue on their merry little way. As we increase the temperature of a reaction vessel, there is more likelihood of an effective collision happening. Okay, so if we see here, we see T1 and a T2 curve. Okay, so it says here that T2 is greater than T1. So most particles actually have mid-level energy, not enough to actually cause a reaction to happen if they collided. So the fraction underneath here would show how many particles are able to actually have an effective collision and produce a reaction. Now when I heat them up, I know it gets lower here at the top, but it just means that the more particles are actually centered closer to having the correct amount of collision energy. And when we take the area underneath this curve, it shows that there are many more particles that are actually having effective collisions, which leads to a reaction. So the more movement a particle has, the more kinetic energy it has, and the more likely it is to react. Now these diagrams should look familiar. We have an enthalpy diagram here for the boiling of water, changing it from a liquid to a gas. This takes 40.65 kilojoules of energy, so we know it's endothermic, and we actually have to climb the hill for this reaction to happen. Okay, so just a reminder about what these diagrams looked like. Okay, so now this diagram looks similar yet a little bit different. It actually shows a hill, and it'll show a hill even if it is an exothermic reaction. We call this an activation energy diagram. Okay, so this shows the energy it took to rearrange particles within the reactants to make our products. Okay, now we know that it takes a little bit of energy for a reaction to happen. We have to put a little in and we might get a lot out, or it might not give us very much in that respect, being endothermic. So this diagram shows that activation energy. So it shows here that if I am following the reaction progress from reactants, I put in a little bit of energy to make this activation complex. So at the top here, we've made some sort of like midway product. Okay, so it took a little bit of energy to get there, and then lots of energy was released. So it shows here that the difference between the reactants and the products will still be the enthalpy change. Okay, the enthalpy change will not differ in any way. However, now we show that extra little bit of energy called the activation energy, and it's represented by EA. And so that just shows the little hill that it has to go over. So not everything can make a reaction. This shows that collision energy, or the fact that not everybody is making products. So this activation complex, or we can also call it the transition state, is very unstable. You will never be able to isolate it. We just know that it exists. This happens for both endo and exothermic reactions. It's just that the reactants and products would have different energy height if it were endothermic. Okay, so the enthalpy change overall wouldn't be negative. It would be a positive one. Alright, so again, these are a little bit different than our enthalpy diagrams in that they show that activation energy required. Okay, the enthalpy is always the same, and you can actually never tell what the activation energy is just based on its enthalpy. It's something that we have to do experimentally, where we're measuring rates of reaction and deciding how much extra energy it took to get that reaction to start. We will never be calculating the activation energy in this way. We'll just be doing some simple math to show the activation energy calculations later on here. Alright, so if we draw our own activation energy diagram here, we're going to do it for the formation of liquid water. So we know that the formation of liquid water is actually an exothermic process. So if I draw the forward reaction, so the formation, I'm going to want to have that negative enthalpy change there. Okay, so my reactants must have more potential energy than my products. So I would start with my reactants here. And I'm going to show an activation energy because I know it takes a little bit of energy to start that reaction, and that overall it is exothermic. Okay, so I can label my diagram here as my reactants and my products. My activation energy is the distance between these two lines here. So between my reactants, where they've started, and the top, which is my transition state or my activated complex. So this is my EA. And this is now my enthalpy change, so delta H here. The difference between my reactants and my products, it has nothing to do with the activation energy. Now, if I want to represent the reverse reaction, so the decomposition of liquid water, this is an endothermic process, meaning that my enthalpy change is positive. So what we would do is we would start with our reactant, so liquid water here, and we go up to our transition state and down to our product. Okay, so here, again, are my reactants and my products, and my enthalpy change is still the same. However, it's positive now, so we're going up towards my products. And the activation energy is not just that small hump anymore. It is from the very bottom where my reactants were to the very top of the diagram. So this is my EA. Now if you notice, the forward reaction, so let's say the production of water here, the enthalpy change forward and the activation energy added together is the activation energy for pretty much the reverse reaction here, okay? And so this is the kind of math we're going to be doing just to show activation energy. Alright, so the activation energy, we will say forward would mean this reaction. When I talk about the activation energy in reverse, it means going from products to reactants. So the activation energy in the forward reaction and the enthalpy can be combined to become the activation energy in reverse if this was an exothermic reaction to begin with. Now, if it were endothermic, it would actually just be the opposite. So we would have been starting down here, going all the way to the top and staying here. And so we only want to actually count that little area for the activation energy in reverse, so we would just subtract the two. Alright, so I just wanted to take a quick moment here and explain that activation complex, or activated complex, transition state, whatever you'd like to call it. So if we have two initial reactant molecules here, when they are reactants, they are separate, but they're moving all the time. What happens is they collide, and when they collide, they start to form these half bonds here. Okay? Now at the very top here, the bonds are both half formed and half broken between those two compounds. Alright, so they're all kind of connected in that respect. Now, after the transition state, the one bond is becoming elongated, the one that's going to leave, and the one that has just formed is becoming a little shorter, more like a real bond, and at the end, at our products here, they have totally separated. So that activated complex is just a combination of those two molecules together. Bonds are both being made and broken at the same time, and you can see that carbon wouldn't necessarily be happy there. It's breaking its octet rule, but but those are just half bonds on each side. Alright, so the bigger the activation energy, the harder it is to get that reaction to start. And so the slower that reaction would actually be. Okay, so the larger the hill shown in a diagram, the slower the reaction. So what can we do to speed up a reaction? Well, we add catalysts. So we add them on both small scale and industrial scale to use less energy to get a reaction to go and to also increase the rate of that reaction. Okay, so catalysts increase that rate of reaction without being consumed. So they're regenerated throughout the reaction, and they only change the activation energy pathway. So they will lower that hill, make it a smaller hill, but they will not change the enthalpy of that reaction. Alright, so I've shown a diagram here for a catalyzed and an uncatalyzed reaction. So we start with our initial reactants and our final products. They will not change with or without a catalyst. We also have a transition state. Now, without a catalyst, we have a fairly large activation energy. Okay, when we add a catalyst, it's lowered that activation energy, but our reactants and products are both at the exact same place, so our enthalpy change does not change. Okay, now we always show progress of the reaction, so from reactants to products, not time, because if we had a catalyst that would wreck this little diagram, we would get something very different. So it's not time, it's always just the progress from reactants to products. So when we added the catalyst, did the activation energy in the forward direction change? Well, yes. So initially, it was a very large activation energy, and in the end, it is a very small activation energy. So yes, it did. It lowered the activation energy in the forward direction. Now, if you were looking from the reverse direction as well, you would see that if you were going from products to reactants, so the reverse, with a catalyst, it has also lowered that. Okay, now the enthalpy change did not change at all with the catalyst and without the catalyst because my reactants started at the same space and the products ended the same as well, so the difference is just the same. The rate of the forward reaction was also decreased with the addition of catalyst, and the rate of the reverse reaction would also be reduced because that hump is smaller to get over. Alright guys, that's it for this unit. You can finish up the rest of your demand line here. Remember that anything that's been indented is not for marks, and I never count the challenge question for marks. Your unit test is Thursday, and your HESIS lab is due tomorrow, so don't forget to share that doc with me.